lecture, we will learn about lecture first. After that, later, baru we will do the practical.
Okay.
Okay. Okay. So have you guys have class previously?
We have class before lah. Yeah.
Oh, until what time?
Until 1:30.
Oh, so you guys already lunch lah? Already had your lunch?
Me haven't lah, but I eat after this class lah.
Okay. You can eat lah during this class if you really are hungry. It's okay because you are just listening kan. Okay. So for this session, we will learn about the computer memory, which is in lecture 4. So can you guys see my screen?
Yes.
Okay. So previously we have learned the CPU and then the basic architecture of the computer, which it has CPU, input-output devices, and memory kan. So now in this lecture we will learn and then we will go into deep about the computer memory. Okay, so start. So in this lecture, we will learn about some characteristic of computer memory, and then what is the meaning of memory unit. After that, we will learn about 3 approaches to enhance the memory performance. After that, we will learn about virtual memory. Okay, so we will proceed to the computer memory characteristic. Okay, so your computer memory also can be called as working storage. So it is referring to your RAM, the RAM of your computer, and then it holds the program and data for access by CPU. So this RAM is only used by the CPU, and then programs and data are stored in memory while processed by the CPU. Okay, so all of when you are opening your laptop and then you are turning on your laptop, your computer, and then you are begin do or opening some applications, and then all of the application will be stored in the RAM while it is processed by the CPU. Okay, so this is the visualize diagram for the RAM. So in your RAM, actually it is divided by each cells. So each cells containing 1 byte data. 1 byte equal to 8 bit. Okay, so your memory or your RAM consists of large number of storage cells. It is sequentially numbered and individually addressable. So each of these cell it has its own number and then it can be addressed. Okay, so the basic size of the cell is typically 8 bits, which is 1 byte. And then when you are storing a large data, for example, 2 bytes of data, or for example, a character that some character may occupy until 2 bytes storage. So the data will be stored in more than one cell. Okay, so for one character, it may be stored in more than one cell or more than 2 bytes of storage. Okay, so this is the the memory hierarchy. So I will go to the more detailed diagram, which is here, because the diagram showed in this lecture is not very detailed. It only has 3 hierarchy, but actually it can be like this. This is the more detailed computer hierarchy. Okay, so at the bottom is the larger memory lah, larger type of memory. Okay, so there are a type of memory that can store large size because it has a very large capacity, and then it can be stored your data even we turn off the the power, the no electricity provided to that memory. So the example of this kind of memory is tape backup. If you know the cassette, you know kan cassette.
Oh
Have
yeah,
you
very old.
yeah yeah. It is very old, but it is very you can store data very long time in that tab. That's why some of the organization are still using tab because the data you stored in tab it can last longer than the hard disk apakah. So it's still, although it is very slow and then it is cheap, but it store your data longer than the other storage. Okay, so the example of this at the paling bottom punya is tab backup. Okay, so the second bottom is hard drive. For example, your hard disk lah. So it is also slow, and then it is considered cheap lah. And then it also can be operate or can store your data even the power to your computer is off. Okay, so it is also can hold large size. And then after that, the flash drive or USB memory. It is also slower and it is also cheap. And then it also can store your data with power off. And then it can hold your data in short term actually compared to the previous two lah. Okay, so sometimes when you do your backup in your flash drive, I think it's better if it is really important. It's better if you do the backup using the tab or hard drive lah, because hard drive is longer than flash drive or USB. After that, so here comes your RAM. This memory only can store your data when your computer power is on, and it is very short term. It can only store your data when your computer power is on. After, when you off your computer, all of the data inside the RAM will be hilang, lost. Okay, so it is fast, very fast, but still affordable. It is not that expensive. It is fast lah. Okay, so it can store medium size of data. If I'm not mistaken, current RAM is up until 12 RAM lah. Tell me if you find uh, apa tu lagi besar punya size of RAM. Okay, so what I know now is RAM can up until 12 RAM. Okay, so after that, there's a processor cache. Okay, so this processor cache is we will learn one type of it later in this slide. So it is very fast but it is very expensive. So it can hold the data in immediate term. Just sekejap saja lah. It is shorter than RAM. It is very small size, and then also it can hold only small capacity, but it is very fast and it is very expensive. So the example of processor cache is like the memory cache. Like if you remember last time we have learned in our IT fundamental class, there's a L1 cache, L2, L3. Okay, so that is the example of this type of computer memory. So after that, the processor registers. It is very fast and very expensive. It can hold smaller size than the cache, than the processor cache. So the example is the processor registers lah, that what we have learned in our previous lecture, the registers that containing the EAX lah, yeah, what you have learned in our previous lecture lah. Okay, so after that we proceed to the computer memory type, which is the volatile and non-volatile memory. So this one, I am sure you guys are already learned. We already learned this in IT fundamental in the last semester. So there are two types of memory, which is volatile memory and non-volatile. Okay, so volatile memory, it can hold data temporarily while the CPU is processing them. Okay, so it can only store the data when the power is on. Okay, so the non-volatile memory is it can hold the data permanently. Okay, so another characteristic of volatile memory is it requires constant power to maintain the stored information. So it means what I said just now lah. It can only store the data when your computer is on, when the power of your computer is on. So for the non-volatile, it doesn't need or it doesn't require any constant power to maintain the stored information. Okay, so the example of volatile memory is the um, RAM, and it is used as a primary storage. And then the non-volatile is the example is ROM, so it can be used as secondary storage. Okay, so these are the two types of RAM, which is dynamic RAM and static RAM. So for the DRAM or dynamic RAM, it is most common and it is cheap. And then its characteristic is it must be refreshed or recharged with power 1,000 per second of time each. Yeah, 1,000 per second lah. It can process or it yeah so the power need to charge is 1,000. I don't know the what to measurable units here. Okay, so I will get back to you guys later lah about this lah. Okay, so about the SRM, it doesn't need the periodic refreshing. It is fast. It has faster access time and more expensive because static RAM is what cache memory is made of. So the top two in the computer hierarchy previously is made of SRM, static RAM. So it is frequently small amount used in the cache memory for high-speed access use. So this cache memory is used by the CPU. That's why it is high speed. Okay, so there are two types of ROM here, which is EEPROM. So it is stand for electrically readable programmable ROM. It is slower and less flexible than flash ROM. And then for the flash memory, it is faster than this, but more expensive. So it is usually used in digital camera, and then it is also used in the BIOS. So BIOS is usually the program in the BIOS is usually stored in flash memory, and so you know about the BIOS, right? We have learned that in the IT fundamental previously. Okay, you remember BIOS?
Yeah.
Oh,
Yeah.
that one.
Okay. So the information that or the program that we boot previously when we are doing the BIOS booting last time, it is stored in flash memory. It is individual memory, or it is individual component inside your computer that only containing small size and all the BIOS. That's why your BIOS doesn't really have a very good interface, except Vera punya BIOS last time. Maybe your computer is a little bit upgrade, so that's why your BIOS have more space. I think that's why it can store some interfaces. But for Kelvin and Noel, if I remember, your BIOS is same like me, just a blue screen with some words kan. And then you also need to use your cursor to proceed or to move your cursor from one instruction to one instructions. But if I'm not mistaken, Farah, you can click, right? Farah, your
Yeah,
BIOS?
can.
So that means that your BIOS storage or your ROM is has more space lah than the BIOS used by Noel, Kelvin, and me last time. Okay, so we proceed to the memory unit. So what we called as a one memory unit is it has the MAR, which is the memory address, and then memory data register. So if you remember, this part is a part or one, sorry, it is a part from registers, right? If you remember last time in our last lecture, so this is can be considered as part of memory unit because it is used as the end interface between the CPU and the memory. Okay, so how instructions and data can be retrieved from the memory by using um, the MAR and MDR from CPU because these two part is storing the address and the data that is inside the memory. So, guess this is the explanation of MAR. So this MAR it holds the address in the memory for which to be open for the data access, and then the MDR is it store the content of the address that is stored in the MAR. Okay, so the word size that can be retrieved or stored into memory in a single operation is determined by the size of the MDR. Okay, so the size of the MDR can determine the word size that can be retrieved or stored into the memory. Okay, so what it is called as a one unit of memory, a memory unit, is actually the one memory unit is consisting of MAR, and MDR from the register or CPU and the memory or your RAM. So this set is called as memory unit. Okay, so what is the relationship? How the MAR, MDR, and the memory is connected to each other is I think you guys can understand more when we open this video or watch this video. This video is telling on the detailed process of the machine cycle. Last time we have learned about the machine cycle, which there's the execute, fetch, and decode too. Okay, so this video will explain how the MAR, MDR, and memory connected or relate to each other by going through the process of machine cycle. Okay, so I will copy paste this. We watch this first. This video is less than 10 minutes. So you
Like
guys
that.
watch this first lah.
Take
Okay?
the con. Let's consider what's going on inside the central processing unit when a stored program runs. namely the fetch, decode, execute cycle. First, let's consider this single
Okay,
line
guys,
of
you watch
code
this
which has
first,
been
huh?
written in a high-level language.
Okay.
You should be able to get your
Okay.
head around that. Take the contents of variable x. Let's consider what's going on inside the central processing unit when a stored
You open
program
your own
runs,
link lah because
namely
you
the
cannot
fetch,
hear the voice. I mean, it's better. It is louder when you open it using your on YouTube.
Let's consider what's going on inside the central processing unit when a stored program runs, namely the fetch, decode, execute cycle. First, let's consider this single line of code which has been written in a high-level language. You should be able to get your head around that. Take the contents of variable x, add y, and store the result in z. If I was going to write something similar in an assembly language, I would need more commands. I need to think about the accumulator. So what we're saying here is load the contents of memory location 10 into the accumulator. Add the contents of memory location 11 to whatever's in the accumulator, and then store whatever's in the accumulator back into location 12. Referring to memory addresses by numbers is called direct addressing. Some assembly languages will allow you to use what's called symbolic addresses. So for example, I might say load x, add y, store z. That depends on the language. Once my assembly language source code has been turned into machine code, specifically once it's been assembled, it might look something more like this. You can see here we're using 6 bits for the operation code and 10 bits for the operand address. You might find something like this in a very old 16-bit machine. Now let's think about the registers inside the CPU. The blue box shows the CPU, and we can see inside there we've got a control unit, we have the accumulator, and the arithmetic and logic unit. We've also got some other registers, the program counter, the current instruction register, the memory address register, and the memory data register. And we're going to take a look at how these different registers cooperate to run the program. You can see on the right hand side I've got the memory, and the program has already been stored in memory. Now I think we need to take a reality check at this stage. First of all, the accumulator is actually a register which is part of the arithmetic and logic unit. But for the purposes of this demonstration, we've separated them. Secondly, the program wouldn't be stored as assembly code as shown here. It would be the machine code that's inside the RAM. The memory addresses themselves would also be in binary. And to tell you the truth, we'd be numbering from the bottom up. But for the sake of this presentation, we've distorted the reality a little bit. So what happens when a program runs? To begin with, the program counter stores the address of the next instruction to be fetched. In this case, the first instruction, which you can see is in memory location 100. Before we can fetch the instruction from the RAM, that memory address has to be placed into the memory address register. Once this has happened, the contents of that memory address can then be loaded into the memory data register. So we're fetching the first instruction now. Next, that instruction needs to be placed inside the current instruction register. Once it's been fetched into the current instruction register, the program counter will increment by 1. So the program counter is always pointing to the memory address of the next instruction to be fetched, before we've even executed this one. Now we can decode the instruction. And without going into detail, the control unit comes into play and it opens various pathways. The next stage in the process is to execute that instruction. The instruction is load 10. In other words, load the contents of memory address 10. So we're going to fetch something from memory address 10. So memory address location 10 now goes into the memory address register. Then we can take the contents of memory location 10 and place that into the memory data register, overwriting its previous contents. and then the contents of that memory address can be placed into the accumulator. That's the first instruction executed. Now we're going to fetch the next instruction. The program counter is already pointing to the memory address of the next instruction, so that memory address can be copied from the program counter into the memory address register. We can then take the contents of that memory location and put it into the memory data register. Now it will move into the current instruction register, ready to be decoded. But before we do that, we increment the program counter, so it's pointing to the next instruction. Okay, so it's time to decode this instruction. So add 11 is passed to the control unit, various pathways are opened, and the control unit makes sense of the instruction. So this instruction says add the contents of memory location 11 to whatever's in the accumulator. So this is where the arithmetic and logic unit really comes into play. An add instruction is passed to the ALU. The contents of the accumulator are moved to another place ready to be worked with. Now we can get the contents of memory location 11, and because we're going to fetch something from the memory, that memory address has to be placed into the memory address register. Once that's happened, we can get the contents of that memory location and place it into the memory data register. You're probably starting to see what the memory address register and the memory data register do. Whenever we want to get something from the RAM, or move something into the RAM, as we'll see in a moment, we must put its memory address into the memory address register. Whenever data, or a program instruction, moves to or from the RAM, it goes via the memory data register. So we have our number 3. That gets placed into the accumulator, and then the arithmetic and logic unit will add that to the 2 that we originally had and place the result back into the accumulator. So we're keeping a running total. It's accumulating the result. It might be worth mentioning at this stage that the circuits inside the arithmetic and logic unit are called adder circuits. They're actually very simple. The truth is, a computer is just a very sophisticated adding machine. Okay, so now we're ready to get the next instruction, which is in location 102. So the memory location 102 is copied into the memory address register. The contents of that memory location, in this case the last instruction, are copied into the memory data register. This instruction moves into the current instruction register. You can probably see what's going to happen next. We increment the program counter. We would probably have a stop or a halt instruction in that position. Now we can decode that instruction, which basically says store the result in the accumulator back into location 12. We're going to put something into location 12, so that memory address must be put into the memory address register, and the contents of the accumulator move via the memory data register into that memory location. And that's our program complete.
Okay, so you guys finish kan? Okay. So can understand a little bit how the process fetch, execute, and decode happening.
There's a lot of steps for each sequence. A lot of steps to do.
Oh, yeah. But yeah, a lot of step lah kan. But it is, I think, better. That's why I keep showing you guys a video, because I don't know if you guys lah, but for me, I learn better when I watch or something that I can visualize or imagine. So how about you? Can you understand? It is either it is better for you learn using video, or just reading can make you understand already.
Maybe a picture with arrows with numbers, like which arrow is first step and then which arrow second step, like that.
Oh,
Maybe.
so you better something yang static lah. It is not like a video lah.
Yeah, static picture with arrows. Like first step, do what. Second step, do what. Third step, do what. Like that.
Okay. How
Oh, what?
sorry. Um, I muted my mic previously. Okay, so how about Farah and Noel? What kind of learning? What type of learning style you guys have? I mean, yeah. What is the because if you know kan a person there are various style of learning. Every person has different type of learning. So for me, I think I am a visual learner lah. So how about si Noel? Okay, wait guys. Sorry ya.
Okay.
How about Noel and Farah? Kalau si Calvin, maybe you are in type of there are three types here, but I think you are actually there are a lot. Maybe you are in visual lah, I think also. Okay, Farah visual. Noel?
Um, Visual and audio.
Oh, so meaning to say that watching video is make you understand more lah, Noel.
Oh, yeah.
Okay, so Farah also the same. So Kelvin, he wants the static one, the static graph or diagram with apa. Okay, so I think it is also a visual, but for the combination is like Noel, Farah, and Mila because I like when there's some voice behind each of the visual that I see. Eh, so okay, so after that we proceed. So that's why I keep showing you guys a video. But I hope Kelvin can understand lah. If you want the step, I think you can pause the video. Yeah. You can pause the video and then you can um, pause and then screenshot and then put in your in maybe slide PowerPoint. Okay, so what I want to say here. Okay, so for a memory unit, it is consisting of a memory and then the MAR and MDR. So this is a memory unit. So maybe Kelvin, later you can screenshot each of the step here if you want to understand more.
Okay.
Okay, so like what the video had said, MAR it is storing the address, each of the address of the data or address of the memory lah, which the data is located in the memory, and then MDR is storing the data. So you can see A address, D is data. Okay, so it will store here. So this one is the process of program counter, so it has the responsible to move to the next phases, and then the CIR is responsible to decode any data or instruction stored in the MDR. It will decode and will post to control unit. Okay, so I think that video can describe better for this the relationship between the MAR, MDR, and the memory. So you can so this is actually the what happening in deep of the MAR and the MDR, but this one has different visualizations lah. Than the video, a little bit different saja lah, but because here it says this is, just imagine that this is the memory, and then in the memory address register in the CPU, in the MAR, maybe it will store something like this. Okay, so after that, this address decoder will decode this data into more understandable, or it will decode lah this one. Before we will see that for example, this is the address of the memory, so meaning maybe the 49 is the address of here, this part, and then this part, and then the MDR will store the data inside the 49 punya part here, segment of the memory here. And so that is how the MAR and MDR. So it is better in that video lah. Okay, so this is for example in the location of 49 in the memory. So how it will store the 101010 ni is by the switch. It will be the value will be 1 if the switch is on, and then the value will be 0 if the switch is off. So by using that switch, the on and off of the switch inside the memory. So you remember inside the memory there's a switch that telling 1 or 0. So by using that memory, the MDR will read and store the data. Okay, so this is the individual memory cell, meaning this one, just imagine this one is the zoom out of, the zoom in of this one, each of this cell. Okay, so each of this cell has a switch. Each of this cell we call as individual memory, individual memory cell. So there's a switch there. So this switch yang akan kasih determine either it is 0 or 1 lah. Okay, so this is what is happening when the read operation happening. I mean, when the read operations, when we read from memory. So first, the memory will copy the address of the memory to be accessed into MAR. Okay, so after that, CPU will set the read or write switch on to indicate a read operations. After that, CPU will set the activation line on to start the data transfer. After that, data will transfer. The transfer takes place, retrieving the data from the specified memory, from the specified memory location, and store it into the MDR register. After that, the data is copied from the MDR into another register, depending on the type of the read data. Okay, so this is actually just stating out what is happening in the video just now lah. Okay, so this is what is happening during the write operations. So first, memory will copy the address of memory to be accessed into MAR, and then after that, CPU will copy the data into MDR. After that, the CPU will set the read or write switch off to indicate a write operation. So there's actually a process inside the CPU that can switch off or on the read or write operation. Okay, after that, the CPU will set activation line on to start the data transfer. So that the data transfer takes place to store data into the specified location memory. So if you can see that the write operation is the opposite of read operations. Okay, so memory enhancement. So this topic, we will learn about how the speed of reading or write the memory can be enhanced. So it will be used three approaches. Okay, so the first approaches to enhance the speed or the operation of read and write from memory to CPU can be enhanced is using wide path memory. This is the first approaches, and then after that the memory interleaving approaches. After that the cache memory. So we will move to the first approaches, which is wider path memory access. Okay, so by use these approaches, makes several bytes or word can be read or written between CPU and memory with each access. Okay, so words here is equal to 16 bits. If you remember, last time we have learned in our what this one lecture 7. I think this is our first practical, our practical class. We have learned about this. So there's definitions of each of these words. So a word is 16 bit. Okay, so um, this wide path memory access, it makes several bytes or words can be read or written between CPU and memory with each access, meaning your bus. So these bytes can be separated as required and processed in the usual way. Okay. After that, this approach can increase the complexity in locating memory address. Hence, fast memory access become more difficult. Um, this approach is widely used because of its simplicity. Okay, so this one kan the what it means is sorry. Okay, well, what it means is it can retrieve multiple bytes instead of one byte at a time. Okay, so that's why it says here that wider path, meaning your bus can carry more than the buses too can carry more than one byte at a time. So that's why you the operation read and write from memory and CPU can be faster because it can carry more information at one time. Okay, so we proceed to more memory interleaving approaches. So I think this one I have found a video also to make us understand more about how this approach can speed up the process of read and write from memory to CPU. So you guys can watch this first lah. It is also less than 10 minutes video.
Hi everyone, my name is Richa. Hi everyone, my name is Richa Thakur, and like majority of the technological enthusiasts, I am also very fascinated by the lightning processing speed of the computational processes. Now, with smarter architecture, like higher clock frequencies and deeper pipelining process, the processing speed has become so fast that it has become a
Okay, so
challenge
you guys
to
watch this
match the
first, huh?
speed of
I
the
have
memory
posted
with the
the link
processing
in
unit
our chat.
Data.
Okay.
and deeper pipelining process. The processing speed has become so fast that it has become a challenge to match the speed of the memory with the processing unit to feed the data. This mismatch in the speed of the memory and the processing unit, also known as the von Neumann bottleneck, reduces the overall optimal utilizations of these high-end processors. To to reduce this mismatch, the memory has undergone several transitions. One such early transition was memory interleaving. And in this video, I'll be focusing on memory interleaving, how memory interleaving works, what are the different types of memory interleaving, and their advantages and disadvantages. So now let's have a look what memory interleaving means. Memory interleaving is a technique to interleave or assign successive memory addresses across multiple memory units. That is, consecutive calls in the address space are assigned to different memory banks. After a memory chip is accessed, usually there is a delay before that chip can be accessed again. This delay is long enough to put a wait state in a fast CPU. However, with memory interleaving, as the subsequent addresses are interleaved among memory units, each unit takes turns to handle the request from CPU while the other is recovering from the access. So when the first memory unit is sending data to the CPU, the second unit will receive the address from CPU. Similarly, when the second unit will send data, the first unit can be accessed again. As a result, the delay between accessing the subsequent word is reduced considerably. Before digging deep into memory interleaving, let's have a quick look at the memory units. The main memory comprises of these kind of sticks. For a DIMM based SDRAM, the front view and back view forms the DIMM, that is dual in memory module. Collection of chips on each side of stick is known as rank, and these rank consist of DRAM chips. Now each DRAM chip can further be divided into memory banks, and these memory banks are the two-dimensional array that consist of rows and column. The intersection of row and column is called cell, where data is being stored in a matrix form. The memory interleaving can be implemented at various levels of memory organization, like there can be rank-based memory interleaving, chip-based memory interleaving, or for multi-channel memory, there are channel-based memory interleaving. But the most basic unit from where this memory interleaving started were banks. So for the rest of this video, I'll be focusing on bank-based memory interleaving. So in bank-based memory interleaving, the main memory is divided into memory banks. An abstract architecture will look like this, wherein the memory addresses are interleaved across these banks. Now let's look at an example to understand the difference between an non-interleaved memory and an interleaved memory access. As you can see, in a non-interleaved memory access, the memory addresses are accessed only when the previous memory access is completed. However, in an interleaved memory access, the access of subsequent memory addresses interleaved across banks can be overlapped. As a result, the overall access time for same amount of data is reduced considerably. Let's understand this by considering cycle times. So assume that it takes one cycle to send the address to DRAM, 5 cycles to access one word from DRAM, and 1 cycle to return the data. So to fetch one word from DRAM, it would require 7 clock cycles as shown in these calculations. So in a non-interleaved memory access, if we are fetching 4 words from DRAM, it would take 28 clock cycles as shown here. However, the same 4-word fetch in an interleaved memory access would take only 10 clock cycles. This shows that the access time is reduced considerably in an interleaved access. Now, the next concept to understand is n-way interleaving. The way of memory interleaving is determined by the number of memory units or banks in which the main memory gets divided. For example, the first figure shows two-way interleaving, as memory is divided into two banks. The second one is a four-way memory interleaving, in which the whole of main memory is divided into four banks. Similarly, for n-way interleaving, the whole main memory will be divided into n banks. Now let's see the different types of interleaving. There are two types of interleaving, low order interleaving and a high order interleaving. In low order interleaving, the least significant bits of the address is used to select the bank, and high order bits are used to select the word in the selected bank. In this type of interleaving, subsequent memory addresses are spread across the banks. However, in high order interleaving, the most significant bits of the address is used to select the bank, and low order bits are used to select the word in the selected bank. In this type of interleaving, block of successive memory addresses are interleaved across banks. Now let's look at the types in detail with the help of an example. Consider that a memory is divided into four banks. As shown here, being a lower order interleaved, subsequent memory addresses are interleaved across the banks. So when the CPU will send the address, the lower bits of the address will select the bank, and the remaining higher bits will select the word that needs to be fetched. In this example, as there are four banks, so 2 bits will be required to select the bank. The lower order bits 0, 0 in the first case will select bank 0, and the remaining bits will select the word within bank 0. So after the first cycle, the state of the system will look like this. And in subsequent cycles, the fetching of data and the selection of bank and word will overlap. For high order interleaving, let's consider the same 4 banked memory with the only difference that block of successive memory addresses are interleaved across the banks. So when the CPU will send address, the most significant 2 bits will select the bank as shown. The MSB of the address, that is 00, will select bank 0, and the remaining lower order bits will select the word from the selected bank 0, here in our example. This high order interleaving is best suited for shared memory systems when the first processor is accessing a bank. At the same time, another processor can access another bank. Let's look at their advantages and disadvantages. For low order interleaving, in burst mode, reads from sequential location can overlap latencies related with accessing each word, as we have seen in the example where we calculated the clock cycles. Also, in low order interleaving, as sequential addresses are interleaved, better load sharing between banks is achieved. And its disadvantages are non-sequential reads may lead to bank conflicts, and failure of single bank may lead to failure of entire DRAM chip. On the other hand, the advantages of high order interleaving are better parallelism is possible since CPUs in shared memory system accesses banks simultaneously. It also provides better resilience to entire system failure. And its disadvantages, it does not support pipelined block access of contiguous memory locations. So, can we combine both the types of interleaving for better performance? The answer is yes. High order interleaving can be done at chip level to provide better parallelism, and low order interleaving can be done at underlying bank level to overlap latencies for sequential read. To conclude, some of the key points are: memory interleaving technique is used in main memory. In low order interleaving, memory conflict can arise if subsequent memory address accessed by CPU is in the same bank, which is called as bank conflict. For shared memory with high order interleaving, memory conflict can arise if multiple processors are trying to access same bank. In current main memory technologies like DDR, memory interleaving is available as optional technique, especially for burst mode. A wider memory and wider cache was considered as an alternative of memory interleaving. Finally, these are the references, and I would also like to thank my professor Dr. Christoph Tuscher for his explanation during the class. And that's all, folks. For any further queries or feedback, you can mail me at rthakur@pdx.edu. Thank you.
I'm done.
Okay, done. Actually, I have to admit this video is a little bit too deep but actually what you because we didn't go into deep in this lecture about the type of the interleaving, and then what we you just need to know is um but actually I didn't find a good video rather than this one, because I keep searching for a good video previously, but I think this is the best lah. But later, if I found a better video that can explain memory interleaving better, I will share with you guys. But currently, this is the best, although um, it is a little bit too deep. So, but if you guys can find any other video that you can share with me too lah, because if you see here kan, a lot of video that is talking about computer organization and architecture are from India. So so sometimes I am having a problem to understand their slang lah, but um, I don't have much choice because the video is from them lah. Kebanyakan the expert in computer organization and architecture are from India. So if you guys later expert in this computer organization and architecture sudah, so maybe you guys can make our own video explaining about each of these item inside or in the computer architecture punya topic. So just tell me lah if you guys find a good video. But currently, what you need to know about the memory interleaving is it is a technique that divide memory into parts. It makes it possible to access more than one location at a time. Okay, so this part or what is bank, I mean in the video just now, it is called as a bank. So each bank or part would have its own MAR and MDR. So that part or the bank from the previous video is actually referring to one memory unit. What I just said previously, one memory unit is consisting of the memory, memory, MAR, and MDR. Okay, so this is one of the memory unit or bank or part. There's different terms used by different person. Okay, so for the memory interleaving, like I just said just now, it is a technique to divide the memory into part or bank or memory unit, and it makes it possible to access more than one unit at a time. So it has its own MAR, each unit or bank or part, it has its own MAR and MDR. And then each part is independently accessible. Okay, so the memory cannot be accessed simultaneously if the locations are in the same block, but it can be accessed if the memory locations are different blocks. So the blocks is referring to one segment. One segment inside the memory is like one row. One row. Okay, for example, this one. This is one row or one block in the memory. Okay, so it says here that the memory cannot be accessed simultaneously if the locations are in the same block, but it can be accessed if the memory location are located at the different blocks. So the blocks is referring to the one row of the memory. Just imagine. Okay, so this is the four-way memory interleaving. It is also said in the previous lecture, sorry, in the previous video. So this one is one banks or one memory unit. This one is one memory unit. This one is one banks or memory unit. This one is a one bank um, or memory unit. So that's why this is COA Memory Interleaving. It has 4 units at one row. Okay, so we proceed to the third approaches of um, memory enhancement. So I also found good. This one I think good lah. Only yang previously yang memory interleaving is not very good because it is too deep. Okay, so but for this one, it is a good video. Okay, so you watch this first. Okay, guys.
Okay.
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 Hey friends, welcome to the YouTube channel all about electronics. So in this video we'll understand what is cache memory in computers and the laptops. So in this video we'll see what is the importance of this cache memory, what is the typical size of this cache memory, and what are the different levels of cache memory that you find inside the computers. So before we understand this cache memory, let us see different kinds of memory that we see inside our computers. So the first kind of memory that we find inside our computers is the non-volatile kind of memory, like a hard disk drive. So this hard disk drive contains a mechanically rotating fast disks, which is also known as a platters. And if you see any commercially available hard disk drive, the typical rotation speed of this disk is either 5400 or a 7200 RPM. So as this hard disk drive contains a mechanically rotating part, so in terms of the speed they are quite slow. So the typical read or write speed that you get with this hard disk drive is in the range of 80 to 150 megabytes per second. But if you see the clock speed of the CPU, it is in the range of 1 GHz up to the 4 GHz. So even though the processor is capable of accepting the data at much higher speed, but it cannot get the data through this hard disk drive at the same rate. And that is where the second kind of memory comes into the picture, that is a random access memory. Now this random access memory is faster compared to the hard disk drive. So this RAM can provide a data to the CPU at a much faster rate compared to the hard disk drive. But still, it is slower than the clock speed of the CPU. So the typical speed of the RAM is in the range of 400 MHz up to the 800 MHz. Still it is lower than the clock speed of the CPU. But if you see the newer generation of the RAMs like DDR3 and DDR4, then they can operate at a much faster rate like 1600 MHz or up to the 2100 MHz. So now if you see the speed of these RAMs, they are comparable to the clock speed of the CPU. So now you may say that these newer versions of RAM can supply data to the CPU at the rate at which they want. But the answer is no. So the modern day processors which we are using are not a single core processor, but they are multi-core processors. So this processor could be either dual core, quad core, or maybe even octa core. So if all the cores are asking for data at the same time, then this RAM cannot be able to deliver the data to all the cores at the same time. And that is where this cache memory comes into the picture. So this cache memory is fastest among the all memories. So now this cache memory is also a random access memory, but it is a special kind of RAM, which is known as a static RAM. So unlike the dynamic RAM which we find inside the normal RAMs, this static RAM is quite fast. And the typical size of this cache memory is in the range of kilobytes up to the megabytes. So the data which is frequently required by the CPU can be supplied by this cache memory. So generally some instructions and some data which is required by the CPU is stored inside this cache memory. So now let us see the different levels of this cache memory. The first level of cache memory is known as a level 1 cache or a L1 cache. So in this level 1 cache, the tiny amount of memory is integrated inside the CPU itself. And all the cores inside the CPU have their individual level 1 cache. So as this level 1 cache is integrated inside the CPU, so they can operate at the same speed of the CPU. And that is the reason the level 1 cache is fastest among the all caches. Now the typical memory size of this level 1 cache is in the range of 2 kilobytes up to the 64 kilobyte. Now inside this level 1 cache there are two kind of caches. The one is instruction cache and the second is a data cache. So the instruction cache stores all the instructions which is required by the CPU, and the data cache stores the data which is required by the CPU. Now let us see the second level of cache. So this cache is known as either level 2 cache or a L2 cache. Now this level 2 cache could be either inside the CPU or it could be outside the CPU. Now this level 2 cache could be separate for all the cores, or it could be shared between all the cores of the CPU. So if this level 2 cache is outside the CPU, then it is connected with a very high speed bus with the CPU. So the memory size of this level 2 cache is in the range of 256 kilobytes up to the 512 kilobytes. But in terms of the speed, they are slower than the L1 cache. Now the third kind of cache is known as a level 3 cache. So all the processors do not have this level 3 cache, but some higher end processors have this level 3 cache. And this level 3 cache is used to enhance the performance of this level 1 and level 2 caches. Now this level 3 cache is shared among all the cores, and it is outside the CPU. So the memory size of this level 3 cache is in the range of 1 megabytes up to the 8 megabytes for a high-end processors. But it is slower than the L1 and L2 cache, but still it is faster than the random access memory or a RAM. So now let us see the process flow when CPU needs some data. So whenever CPU needs some data, then first of all it will look inside the L1 cache. So if it will not find inside the L1 cache, then it will look inside the L2 cache. And if the data is not inside the L2 cache, then it will look into the L3 cache. So if the CPU finds the data inside the cache memory, then it is known as a cache hit. But if data is not available inside the cache, then it is known as a cache miss. So suppose if data is not available inside the L3 cache, then the CPU will look inside the random access memory or a RAM. And still if doesn't find any data inside the RAM, then it will get the data from the hard disk drive. So when you are starting your computer for the first time, or you are opening some application for the first time, then that data will not be available in either cache memory or in the RAM. So at that time the CPU will get the data from the hard disk drive. But once the application is opened, and then after if it requires some data, then CPU will get the data either from RAM or through the cache memory. Now you may ask that if this cache memory is so fast, then why the size of this cache memory is only in the megabytes? So the reason is that this cache memory is much costlier than the other memories, and that is the reason you will find only a few megabytes of cache memory inside a CPU. So whenever you are buying some desktop or a laptop for yourself, don't only look the random access memory, but also look the how much cache memory that CPU has, because this cache memory decides the overall performance of the processor. And the same thing is applicable for the smartphone processor as well. So I hope in this video you understood what is the cache memory and what is the significance of cache memory inside the computers. So if you have any question or suggestion, please let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.
Okay.
Okay, done.
Yeah.
Okay, so from that video, why do you think the cache memory can speed up the operations of CPU and memory read and write? Who can answer?
Because it's in the middle.
Yes, Noel, can you speak louder?
Because the cache is in the middle, like the middleman.
Okay, so you said cache is act like a middleman lah kan between CPU and memory, right?
Yeah.
Okay, so Farah, why do you think?
I'm not sure.
You cannot understand the video.
Yeah, I understand a bit.
Okay, Kelvin, what do you understand from that video? How the cache can speed up the process?
I'm also not sure.
Okay, so if you guys remember just now in that video, it said that the cache, it is actually memang it is designed for high speed memory, meaning everything that you stored in the cache memory memang akan kena read faster compared to RAM. Okay, so it is physically designed to be high speed, meaning when the CPU read anything from this memory it will be faster, but it is very expensive. Okay, so that's why it is only the size is very small. So because of the size is small also, it makes the reading from that cache is faster because it doesn't need to load a lot of information to search for your informations, because the size is small, and then the design also is designed for the high speed reading or write. So that makes the cache memory um, that makes the read and write operations between the CPU and memory is faster compared to the RAM. Okay, so if you remember, RAM has a larger size card, larger size. So when you stored or when you search information from RAM, you need to search each of the uh, part or segment inside the RAM to search for your info. But for the memory, because it is small and then it is also designed, its physical design is memang designed for the high speed memory. So it makes the read and write operations is faster. Okay, so by adding cache memory between CPU and memory RAM, it can make the process of read and write faster because of that middleman. Same like Noel said lah just now. Okay? Understand?
Okay.
Okay.
Okay, so remember the point, there are 2 points there. First, it is designed. It is physically designed for faster speed memory, and then it is also smaller in size. So it makes that reading the information inside that cache is faster lah. Okay, so this cache memory also, it is invisible to the programmer and cannot be directly addressed in the usual way. So this is it is meaning to say that we cannot address this cache memory like the usual way we address the bus memory. So it has a special way of addressing the info inside the cache memory, but we will not cover that in this lecture lah. Okay, so after that, the cache memory is organized into blocks. So these blocks are used to hold an exact reproduction of a corresponding amount of storage somewhere in the main memory. Okay, so each block holds a tag which identifies the corresponding location of data in the main memory. Okay, so the cache memory also it has the text kan, so the text act as a directory that can be used to determine exactly which storage locations from main memory. Okay, so in the cache there are 3 components that works. First component is cache controller, so it is a hardware that checks the tags. Okay, so after that there are component which is cache line. So this part is the unit of transfer between storage and cache memory. And then after that the hit ratio. So this part in the cache memory is the part that do the ratio of hits out of the total requests. Okay, so this is the the cache controller here. So this is how the cache memory works. So first, it will, the CPU, every memory request goes to the cache controller. So CPU will request the memory from the cache controller, for example, 23334. After that, the cache controller will check the request against each of the tags. So remember, cache control in cache it has a tag. So that tags containing the text is containing the text will act as a directory that can be used to determine exactly which storage locations from the main memory. Okay, so this cache controller will check the request against that directory or the tag. So in this illustration, each line contains 4 bytes. So each line contains 4 bytes starting with the tag address. Okay, so 4 byte, each line of here is containing 1 byte. So each line of here is containing 1 byte. So this is the tag address. Okay, so after that, if there is a hit, the cache location is used instead of the memory. Okay, so the hit the hit here is referring to the process when the request find the info inside the memory. So it is called a hit. Okay, so when a hit is happen, so the cache location is used instead of memory because the location in this cache is where the information is stored in that cache. Okay, so what is happening when there is a miss? So, who remember what is a miss in that video previously? What is a miss?
Like no data.
Yes. Okay, so a miss is when the request from the CPU it has no info. The request has no information from the cache. So if you guys remember previously, if the information cannot be found in L1, it will search. When there's a miss in L1, it will search L2. When there is a miss in L2, it will search L3. When there is a miss in L3, it will find to RAM. When there is a miss in the RAM, it will search HDD. So, but here, when there is a miss, um, um, in this explanation, it says when there is a miss, the cache controller will require a cache controller to select a line for replacement from the memory. So, okay, after that, after which the new line in cache is as treated before. So in this, actually, when there is a miss, it will search the information from the memory. After that, it will, the cache controller will select any part inside the cache controller to place the info from the memory if it find the info from the memory. So after that, it will store the memory that it found inside this cache, and then the new line of the cache will be stored inside this cache. Okay.
Okay.
Okay, so we proceed to virtual memory. I remember last time during the IT fundamental class, I remember Farah has asked me about this. And Farah, do you remember what is actually the virtual memory? You asked me last time.
Yeah.
Yeah, so I think I don't know if my answer last time is really answering your questions, but this video will tell about the virtual memory better lah. Okay, so you watch this video first.
This diagram illustrates the essence of a segmented memory management system. On the left are some of the programs that have been installed on the computer's hard drive. These are just files on disk until they've been launched. In the middle is the computer's physical memory, the RAM. This contains any programs and data that are currently in use. On the right is a swap file on the computer's hard drive. Each program that's currently running might be a procedure or a function. A running instance of a program is called a process. Needless to say, the operating system itself has a number of processes in memory when the computer is working. Suppose the user starts launching applications. Sooner or later, the memory is going to fill up. Notice how different processes occupy different amounts of memory. These portions of memory are known as segments. They're based simply on the sizes of the programs. For each process, the operating system knows its starting location and how big it is, so it knows where everything is. When a request is made to launch some more software, perhaps a word processing application, something has to move out of memory to make room for it. If one of the processes belonging to the presentation software is currently doing nothing, the operating system might decide to move it to disk, temporarily at least, so the word processing programs can begin. When another request is made, perhaps to launch a web browser this time, another idle process of at least equal size has to be moved out of memory to make way. In order for the spreadsheet process in the swap file to start running again, something else of at least equal size has to be swapped out. Although there is enough free space to allow for this, the free space is fragmented. In a segmented memory management system, each process is atomic. It can't be split up. It's all or nothing. So the spreadsheet process is going to have to wait. The chances of the large presentation process getting back into memory are now particularly low, because a number of adjacent processes will have to become idle before this can happen. In summary, in a segmented memory management system, segments are swapped between disk and main memory as needed. Program segments correspond to blocks of program code, such as procedures or functions. Data segments correspond to data structures, such as stacks, queues, or graphs. Segments vary in size. The operating system knows the start and size of each segment in physical memory. Each segment is atomic. Either the whole segment is in RAM or none of the segment is in RAM. A segment in memory can only be replaced by a segment of the same size or smaller. Segmentation can result in memory fragmentation, a lot of small segments with gaps in between. Large segments may not be allowed into the memory very often at all. Segments can be pushed together to limit the amount of fragmentation and allow large segments to be loaded more often. With paged memory, as far as any one program is concerned, it has the whole memory to itself, which of course is not true. But the operating system allows the program to behave as if this is the case. A program's view of the memory is called logical memory. In reality, each program is broken up into a number of equal-sized pages. Each page is only 4 kilobytes in size, so a single page might contain a single program, more than one program, or just part of a program. These pages could be anywhere in physical memory that the operating system decides to put them. Indeed, some pages may be on secondary storage. To make this possible, the operating system maintains a page table with information about which logical locations map to which physical locations. As far as any one program is concerned, the memory is a quiet place. Here's the word processor's view of the memory if it is also running. And here's what the spreadsheet application thinks is going on. The reality of physical memory is, of course, somewhat more complicated. When yet another program, or indeed data, wants to access the memory, it may well be loaded in a fragmented state. If there isn't enough space, some of the other pages will be moved to disk. This is called paging out. When a program on disk is required again, it will be paged back in. Supplementing the RAM with secondary storage like this is called virtual memory. In a busy system, when the memory is almost full, there can be so much paging activity that the computer becomes unusably slow. This is called disk threshing or disk thrashing. In summary, with paged memory, the memory is split up into small, equal-sized sections called pages or page frames. A single application might occupy multiple pages, which aren't necessarily contiguous. Each application program has its own view of the memory. This is called logical memory. A page table records where the different pages of a program are located in physical memory. Unused pages may be paged out to a swap file on disk to make room for others, and these pages are paged back in when they're needed again. Supplementing physical memory with secondary storage is known as virtual memory. When memory is low, excessive swapping can lead to disk threshing, and this can degrade performance. So what's better, segmentation or paged memory? Segmented memory makes an entire block of code available to the processor, which allows for fast access. Segmentation, on the other hand, can lead to fragmentation of free space. With segmented memory, large processors might not get access to the memory very often. Paged memory, on the other hand, can lead to fragmented processors, which will run more slowly. However, paged memory makes better use of free space. Windows uses paged memory. Segmented memory is not as common. Some processors support a hybrid of paged and segmented memory management, in which each segment consists of several fixed-size blocks. The best of both worlds.
Okay.
Okay.
Okay, done. Done kan?
Right.
Yeah.
Okay, so Farah, after watching that video, do you understand what is the virtual memory?
I think I get the concept already lah.
Okay, so what can you understand? I think, I mean, you can just answer whatever you understand, lah. What is the concept that you get?
Yeah, the segmented memory, like it got swapped between this and the main memory, like that lah.
Okay. How about Noel?
Like the memory, like divided into segments for the
Mm-hmm.
for application, like that.
Mm-hmm.
Then if like the memory not enough, then
Mm-hmm.
transfer into the hard drive temporarily.
Mm-hmm. Mm-hmm.
Yeah.
So basically, this segmented, this swap files for like for a while kah? For a while only kah?
You mean the process?
Yeah, the process.
Yeah. Okay, so before that, I will ask Kelvin lagi. So Kelvin, what do you understand about the virtual memory?
Uh,
Just lost segments, and then need secondary memory to fill in. Not sure how to say.
Okay, so I will tell you guys what I understand lah. Okay, so we are all learning here. I am also still learning. So what I understand about the virtual memory is actually, when the first about the segmentation and pages. If you guys aware or realize just now, segmentation when there's a process of segmentations, there's no um, virtual memory created. Only in the process of paging, it has the virtual memory. The virtual memory is actually the logical memory that is created during the paging operation. Just now, if you guys remember this, this one. Okay, so this logical memory and this page table is actually um, created virtually by the memory, but actually it takes the space from your RAM, from your hard drive. It takes the space from your hard drive, and it store the logical memory information and this page table. So that secondary the logical memory and page table too, yang the space it get from the hard drive too, it is called as the secondary storage. So that secondary storage that it gets from the hard drive is what we called as virtual memory. Agree?
Oh,
Yeah. So by the page memory, it is the difference between the page and then the segmentation. Previously segmentation, it doesn't have logical memory, or it doesn't need to create a virtual memory from hard disk, because it is directly from the program to the physical memory directly. If you see the what this one, this diagram. So it doesn't need any logical memory, but for the pages or paging, it needs a logical memory that is created or obtained from the hard drive. To create that logical memory, and then what that is what we called as virtual memory. I hope you guys understand lah. If you don't agree, then you can argue with me later if you watch this video again. I think this video is a very good video lah compared to the memory interleave previously. I can say that this video is very good, explaining the segmentation, paging, and the virtual memory. Okay, so whatever video I shared with you guys, I am not just searching YouTube and then just simply put the video for you to watch, because some of the video I will watch first and then determine which is the best, then baru I share with you guys. So it is good for you to if you want to understand more later, you can watch this video again and again lah. I will share that the updated lecture letter that has the link to the YouTube for you guys later.
Okay.
Okay, so this virtual memory, this is just the summary of what we have watched just now. So virtual memory is a computer is able to conceptually split the address used in a program from the address that identify the physical location in the memory. Okay, so the program address are referred as logical address. So they do not have any reality outside the program itself. So it is actually doesn't stored physically inside the memory. It is only just um, um, it is just all information. It is virtually created saja. It is the information is created virtually, and then it is only containing all of the info. It didn't store that information inside the virtual memory permanently. So it is only temporary, like what Vera just asked just now lah. It is this virtual memory memang temporary. It is only created during the CPU or your computer is running. Okay, so the actual memory address are typical address. Okay, so that logical, it doesn't have any physical address. I mean, it have no any reality outside the program itself. Okay, so the actual memory is referring to the physical addresses in the memory. Okay, so the mapping, virtual storage creates a corresponding between logical and physical address. So that each logical address is automatically converted into physical address during the execution. So as you remember just now in that video, the logical memory is created to store the address of the physical memory. Okay, so the mapping of the logical and physical address is dynamic. So by using this virtual memory, it stores the address dynamically, or it maps the logical and physical address dynamically. Meaning it doesn't need to be macam segmented previously. The segmented you need to if you remember the atomic segment. Okay, I want to ask who understand about the atomic segment. Atomic segment. Yes.
Like cannot split anymore.
Yes, betul. Correct, Noel. Okay, so atomic.
Like what?
Okay. Can Noel say it again?
Cannot split.
Cannot
split.
split. Yeah, split.
Oh, okay.
So atomic segment meaning to say that you cannot split that segment. So if in the memory, if you remember, you watch that you watch the segment part later in that video. So if you remember, if the program that you open requires more memory, and then that sini wait we watch that video again. So atomic. So okay, it means here that each segment is atomic. The atomic meaning is either the whole segment is in RAM or none of the segment is in the RAM. Okay, so by using the segmented memory, you will see here the paget is the difference is in the physical memory. Each of the segment is divided 4 byte each segment. It is in the pages. But in the segmented memory, it will segment your memory based on the size of the application you open. Okay, so for example, this one. This one is the spreadsheet. Can you open maybe more than one spreadsheet? Okay, so you opening the one spreadsheet, but you left the second spreadsheet is in the idle, and then in this segmented memory, you have this. I mean, in your memory, um, there are still free space here. If you see here that this is 2 and then this is 2, and then if you can see here, this is macam correspond to 4 segment kan. Logically, it can be you can open this application using this physical memory, because maybe you can split this one into two here and then two here. But because of the rule for the segmented memory, you cannot split, meaning this segment act as an atomic. Atomic meaning you cannot split it. Okay, so that is the meaning of the atomic clock. You cannot split this, although you have enough free space here. It has to be di sini mesti ada 4 juga to kasih masuk yang ini. If you want to open this, your memory should have the free space yang berturutan di sini. You cannot split that and then put that in the free memory here. Okay, Sarah?
Okay.
Okay, so, okay, Kelvin?
Okay.
Okay. So, where were we? Okay. So that is the meaning of the atomic segment. But from the pages, using the pages segmentation, the page memory, so it can overcome the problem of the segmentation pula, because using the paging, you can store the informations dynamically, because it has the logical memory that stored the address. So even though you stored in physically, you stored that data terpisah-pisah, it doesn't matter, because the register or that information is stored in the logical memory. So it doesn't matter lah. Either you can um, store your data split. Okay, so the mapping of the logical and physical address is dynamic. So this is what it called. It is different from it is opposite of the atomic. So that is the meaning of this dynamic. So it can be changed anytime by the OS to meet the different condition within a system. A memory management unit perform this operation. Okay, so who will do the the mapping between the logical and physical? It is done by this guy, the memory management unit. Okay, so the virtual storage is done in two ways. Okay, so this is the two ways of virtual storage. First is the segmentation, what we have learned previously. So with segmentation, it has a lookup tables which contain the starting address for logical and physical memory and the size of the block. And then the physical location of the particular memory cell is located by adding the offset from the starting of corresponding physical address in the table. After that, so this is for the paging. Who remember just now in that video, Microsoft used what? Segmented or paging?
Paging.
Okay, so Farah, Microsoft used which one?
I think paging.
Noel?
The paging.
Okay, yes. Okay, so Microsoft using paging. Okay, so this is about the paging. So this is managed by the operating system. Okay, so if previously the segmentation, it is okay, so sorry. Okay, we proceed. Okay, so this paging, it is managed by the operating system. It is built into the hardware, and then independent. It is the independent application. Okay, so the size of the block is defined for the system and is identical for every block. So if I remember correctly, each of the block is 4 bytes. Okay, so each logical block is called a page, and then the corresponding physical block is called frame. Okay, so after that, so this is the logical view. This memory management unit is the guy that will handle process of mapping the logical view to the physical view. And then this is the differentiation between the logical and physical address. Okay, so the logical address are relative location of data, instruction, and branch target, and are separate from physical address. Okay, so it is separate from the physical address. So this is the logical memory. So in this logical memory, it contains the relative locations of the data from the physical memory. Sorry, it contains the relative location of data, instruction, and branch target, and then it is separated from physical address. After that, yeah. So like I said just now, each block size is typically 4 kilobyte. I said just now 4 byte, kan? So it is actually 4 kilobyte. Okay, so the block is chosen so that the bits of the memory address can be easily divided into a page number and an offset. Each line of the page table only consists of page number and its corresponding frame number. Okay, so the goal for the virtual storage is to increase the perceived amount of memory available in a system. So when your computer doesn't have enough space, then the virtual storage will help in increase the amount of the memory. Okay, so this logical address provide the important capabilities. Okay, so the important capabilities is the ability of relocating program easily from one part of memory to another. So this capability is very important to do any multitasking. Okay, so after that, the ability to split the program to smaller pieces that can be loaded into different parts of memory. Yeah, so this logical, it is talking about the logical, yeah, this one. So this logical address has the ability to split the program into smaller pieces that can be loaded into different parts of the memory. After that, this one also about the logical address. Okay, so this logical address also provide another important capabilities, which is same logical address of two different programs transformed into different physical location or vice versa. So it has the capability of transforming the same logical address of two different programs into different physical locations or vice versa. Okay, so it also makes the program think itself has more memory than actual exists on the computer. So this is the page address, meaning this is the example of 20-bit address that is stored. That locating or that telling the address of the page. Each of the page has this number. Okay, so it is 20 bit. So the first 1, 2, 3, 4, 5, 6, 7, 8. So the first at MSB is storing about the page number, and then the 12 LSB or less significant bit telling about the offset. Okay, so this is the page translation. How the process of page translations. Let's say your page has this address. After that, frame number. Okay, so if you remember, there's a page table, kan? In our video just now. This one page table. If you guys remember this one, this page table. Okay. So this is the page table. That page table has the page and the frame location. So so this page table containing the page number and then the frame number from the memory. Okay, so the logical address, this is the logical address, this is the page table, and then this is the memory. So this page table is acting or responsible as the middleman to store the information that is telling this logical address is referring to which segment of memory. Okay, so this is very important main lah, because it is containing the data that will tell this logical address to map to which memory, physical memory. Okay, so this is the advantage of the page translation process, meaning this is the advantage of having the page table just now. So the advantage is the program can share memory space. And then because if you remember just now, it doesn't matter. You can store the data dynamically. It doesn't need to be atomic because you have the page table. Okay, so more program run at the same time, and then programs run even if they cannot fit into memory all at once. But the disadvantage is the swap file will take up space on the disk. Okay, so the paging will take up resources of the CPU. When you are doing the paging, the CPU will process, the process in the CPU will be heavy. Okay, so it will make your CPU process takes a lot of, it took time to process in the CPU. Okay, so that's it. Okay, can understand? We are using all of the time, only 4 minutes left. So do you have any questions? If you don't really understand, you can watch that video again. But if you cannot understand juga, you can ask me which part you don't understand. Okay?
Okay.
Okay. So Kelvin, okay.
This chapter very hard.
Very hard.
This subject very hard.
Oh yeah, memang. This chapter memang hard. But for me, that's why I also learn this using YouTube. Maybe because I am the visual type of learning punya person lah. And I think there's one guy in that video that is very good in explaining, but we need a lot of time to watch his video. For example, this guy. Di mana sudah tuh? There's one guy lah, but that why I didn't share the video with you all, because each of his video will takes up until 1 hour punya video. That's why I cannot share with you guys lah, because it is so apa. I will find that video, and then I think you, if you are curious enough, you can follow him, his YouTube channel, because he is very good in explaining the computer organization and architecture. Some of the info that I get from his video. So I will share with you guys later, because I cannot find it. I forgot even his name. I just remember his face.
Oh,
Okay.
okay.
Okay. So guys, if you don't have any question, we can end here.
Okay, Miss.
Okay. Bye.
Okay, Miss. Thank you.
Okay.